This conference will now be recorded.
So very good evening, students. Today we are back with the revision part of JEE Advanced Paper on the topic modern physics, where we'll be taking up questions from atoms, nuclei, dual nature of matter, semiconductor, etc. So let us start our discussions for today. So this is the first question, which is from photoelectric effect. Let us see that. So this question says, for a photoelectric effect with incident photon wavelength lambda, stopping potential V naught, identify the correct variations of V naught, which is stopping potential with lambda and with 1 by lambda. See, whenever we see this kind of graph and all, and to see the variations with any other parameter, let us first of all write down the famous Einstein's equations for photoelectric effect. What is that saying? The maximum kinetic energy Kmax, that is equal to the energy of the incident photon minus the work function. I take that phi. And if we recall, the stopping potential must be equal to energy must be equal to the maximum kinetic energy, that is EV0. And see, in place of nu, we can write c by lambda. So if we do that modification to this equation, what we get? EV0 is equal to hc by lambda minus phi. Okay. If we further, so we have to plot in the y-axis v naught. So we'll keep that alone, and then we'll write here hc by e into 1 over lambda minus w e by phi. Okay. All right. See, if we plot now this v0 versus lambda, then somehow or other you look with lambda, it is varying like, see, if I just for the time being, if I just ignore the intercept part, which is a negative intercept, if we ignore that part, they see the stopping potential and this has this kind of variation, so they are inversely proportional, and the proportionality constant is ac by e. This is a constant, okay, or the slope. So if we plot only v0 versus lambda, it is going to be hyperbolic curve. It is not a linear curve, okay. And this is, see, the first one is giving the hyperbolic curve. You know that pv is equal to RT for ideal gas, right? So if we plot p, so p is inversely proportional to v. So if we plot p and v, we get this kind of curve, right? So similar to this PV curve will get a hyperbolic curve, and with, okay, so with lambda. But if we plot in the x-axis 1 by lambda, if we plot 1 by lambda in the x-axis, then we must be getting a straight line. We must be getting a straight line with positive slope, not negative slope. You look here, this is a positive slope, so we'll get a straight line with a positive slope, okay. And this is having positive slope with a straight line, this is having negative slope with straight line, okay. So A and C will be the correct answer for this question. So this was question from JEE Advanced 2015. Now we'll move on to the next problem. So this is also JEE Advanced 2015 problem. So an is electron in an excited state of lithium. So we know lithium has actually 3 electrons, and when we excite it to 2 plus state, that means it acts as hydrogen-like atom. So this becomes an hydrogen-like atom. That means we can use the Bohr's theory upon it. Okay, so hydrogen-like atom, H-like atom. We can use Bohr's theory, or we can apply because Bohr's postulates and etc. For calculating energy and all those things, we can use only hydrogen. Like we can use the Bohr's theory for calculating energy etc. only for hydrogen atom. So hydrogen atom has only 1 electron in the outer orbit. Okay, or hydrogen-like atom which has, like hydrogen-like atom means any ions can be hydrogen-like atom, like lithium. If I take helium plus 1 ion, okay, plus 1 or 1 plus, okay, 1 plus ion can behave as hydrogen-like atom. So for this kind of atoms, so look, this kind of atom, the energy expression will be actually C minus 13.6 by n square. It will be actually Z by n square. So here there will be Z, okay, Z by n by Z whole square. I think there will be Z square here. Okay, Z square. In place of n, we have to write n by Z whole square. Okay, that's how we'll get the energy. Anyway, so similarly for ready etc., there will be a change. So Bohr orbit, generally we get any arbitrary orbit for hydrogen atom. Bohr orbit is this a n square, but in case of hydrogen like atom, we will have write we have to write a0, this is Bohr radius, n square by Z. This will be the radius of hydrogen like atom. Okay, these are the things we need to remember. So let us see, an electron in an excited state of lithium 2 plus ion has angular momentum 3h by 2 pi. The de Broglie wavelength of the electron is in this state is pi. So de Broglie wavelength is given. So p pi a0, where a0 is the Bohr radius, and the value of p will be how much? You have to find out that. So the question is, say for hydrogen-like atom, we know Bohr's postulate can be applied. So here it is given that lithium 2 plus excited state has angular momentum. We know L angular momentum can be written as nh by 2 pi. nh by 2 pi in general, ln is equal to. So that is here given as 3h by 2 pi. So if we just compare, we'll get the value of n to be 3. That means the lithium ion 2 plus ion is in its second excited state. Second excited state. Okay. So second excited state, n is equal to 3 we have got. Now see, we know de Broglie wavelength lambda d, I am writing here, lambda d will be h by p. P means what? H by mv. So if we multiply r mvr, so here in this particular orbit, what is the value of r? Sorry, mvr means L. So this is h into r by L. L3 here. Ln means n is the orbit. So here it is in the or third second excited state. So L3 it is given as CHR divided by R is the radius of that particular orbit, and this is given as h by 2 pi. So 3h by 2 pi. Then we can just strike this out. So 2 pi R by 3. So this will be the de Broglie wavelength. So de Broglie wavelength we have got as lambda d is equal to 2 pi R by 3. Once we get that, what else we can do? We have to find out the value of P. So we can just compare with this. So 2 pi by 3 R. So this R also we have to write. R is actually A0 N square by Z. So what is this for the lithium 2 plus ion? A0 let it be like this. N is 3, so it is 9 by Z is 3. Okay, so let us write it here. In place of R we'll write, that means it is actually 3 A0. So 3 A0, 2 pi into 3, 2 pi by 3 into A0, and it is here P pi A0. So pi goes off 3 3 A0 A0, so we get P is equal to 2. So this is the value. So value of P is 2. Okay, I hope you guys understood this. So we have to always see for this kind of problem, we have to find out the number of orbit, like which energy state it is in. Then we have to write the de Broglie wavelength and compare it. And at the same time, you have to remember the formula of the radius, okay, radius of that particular orbit in terms of Bohr radius, okay. So then only we'll be able to solve this problem. All right, so we'll go to the next problem. Okay, so this is again a nice problem. So for a radioactive material, for a radioactive material, for a radioactive material, its activity A and the rate of change of its activity R are defined as. So see, activity is A, which is defined as dN by dt, okay, and the rate of change of activity is defined as minus dA by dt. So these things are given, where N of T is the number of, this is I think T, okay, is the number of nuclei at any time T. So N of T is the number of nuclei at any time T. How we write this? We write as N0 e to the power minus lambda into T. This is how we write, isn't it? Okay, so two radioactive sources, one is P, another one is Q. Their mean lifetimes are given. This is tau and this is 2 tau. Have the same activity at t is equal to 0. They have same activity at t is equal to 0. The rate of change of activity is Rp at t is equal to 2 tau are Rp and Rq respectively. Then you have see the ratio Rp by Rq is given as N by E. Then what is the value of N? So it is a very nice question. I think this is yeah, this is also 15th question, 2015 JEE Advanced. Now I'll just explain you the questions once again. The question is that radioactive material of activity A and rate of change of activity, its activity R, is given as A is equal to minus dN by dt, R is equal to minus dA by dt, where N of T is the number of nuclei at any time t. There are two radioactive sources which has, like, one of them is P, another one is Q. P has mean lifetime tau and Q has mean lifetime 2 tau, have the same activity initially when t is equal to 0. Their rate of change of activity is, that means Rp and Rq at t is equal to 2 tau are given. Rp and Rq, their ratio Rp by Rq is n by E, so you have to find out what is the value of n. So look here, it is very simple. So if we write A is what? A is dn by dt. That means, you know, ddt of, so here minus is there already. So ddt of n0 e to the power minus lambda t. Okay, so what we get here? So we get n0 lambda e to the power minus lambda t. Okay, so this is what we get. Okay. Okay, so if we require any time, we can use this thing. Okay, so this I can write as n0, sorry, a0 e to the power minus lambda t. Okay, this is the activity. Okay, this is how activity is written. Now look, rate of change of activity, see, R is equal to minus dA by dt. Okay, minus dA by dt means what? Minus dA by dt. See, we have found out what already what is A. We can write it ddt of a0 e to the power minus lambda t. So this will give you again a0 lambda. Okay, what it will give? A0 into lambda e to the power minus lambda t. I hope you agree with me. Just simple derivative with respect to time. Okay, so this is, let us say this is equation number 1. Now what is given? See what we know actually, Rp and Rq. Let us write what is Rp. If we write Rp, what we can write? We can write this R0, and in place of, sorry, A0, in place of lambda, we can write lambda p e to the power minus lambda p into t. This is what is Rp. Another one is Rq. This Rq also can be written as A0 lambda q e to the power minus lambda q into t. This is how we can write this two. And then say, if I take the ratio Rp, I think there is, yes, Rp by Rq ratio we have to write. So this is A0 lambda p e to the power minus lambda p into t divided by A0 lambda q e to the power minus lambda q into t. Okay, so now see this lambda, we know lambda is equal to, how much? 1 by tau. Okay, so because mean lifetime is like this, so mean lifetime tau is equal to 1 by lambda. So this is how it is defined. So we can just replace the lambda p with tau. So in case of p, see, lambda p is equal to only tau, and lambda q is 1 over 2 tau. This is what we will write here. Okay, so lambda p will be 1 over tau e to the power minus t by tau. Here a0 1 over 2 tau e to the power minus t by 2 tau. This a0 we can strike them out. Okay, then let us clean this first. Okay, so this tau also will get cancelled, so 2 is there, right? So 2, and this is e to the power minus t by tau, and this will be plus e to the power t by 2 tau. That means it will be 2 into e to the power minus of t by this. Okay, e to the power, let me check once again. Oh, t is 2t, 2 tau. The time is given as t is here 2 tau. So we'll write the time 2 tau. So e to the power minus t is 2 tau, and it is also 2 tau. So it is 2 by e, right? So in the question, what was given? Rp by Rq was given as n by e. So what is the value of n here? N is 2. So this implies n is 2. So this is the answer. What is the value of n? N is 2. Okay, we'll move on to the next problem. Okay, this is now an interesting problem. So what is this problem saying? This is, what is this related to, first of all? So this is related to uh, so this is a problem from nuclear reaction, fission reaction. So fission reaction is given as this, as you see here. I may write it here. So the fission reaction says this is U 236, uranium 23692. It breaks into two nuclei, xenon and strontium, 94 and 38, and there will be two more particles, X and Y. Okay, considering uranium 23692 to be at rest, the kinetic energies of the product denoted by Kxc for xenon, Ksi for the strontium, and Kx, the nucleus, unknown nucleus, sorry, unknown, so unknown nucleus of X has kinetic energy 2 mega electron volt, and Ky, kinetic energy of nuclei Y has kinetic energy, the same kinetic energy, 2 million electron volt or mega electron volt respectively. The binding energies of the nucleon of this uranium and xenon, strontium be this. So this is actually binding energy per nucleon. Okay, for uranium is 7.5 MeV, then xenon is 8.5 MeV, strontium 8.5 MeV respectively. Considering different conservation laws, the correct options is or are these. So x and y will be, see, first option says x will be n, y will be n. N means neutron. Okay, x and y both will be neutron. And kinetic energy of strontium and xenon. Strontium is 1 to 29 MeV and xenon 86 MeV. Option B says X be the p proton and Y be the electron. And xenon and strontium has the same kind of energy, same energy. Strontium 129 MeV, xenon has 86 MeV. Then option C says it is proton and neutron, and energies are as given in the above options. And the D says both the particles are neutron with kinetic energy interchange. Like say strontium has kinetic energy 86 MeV and xenon has 129 MeV. So now you have to find out which option is correct. So what are the conservation laws we can use here? See, first of all, linear momentum conservation. Linear momentum conservation. Then you can, first of all, you can just go with charge conservation. Charge conservation, where the charge is conserved. Conservation. Then, then the energy conservation. Energy conservation. Okay, so these are the things you have to, at least you can consider. See, if we go with charge conservation, let us see what should be the charges of x and y. See here, the total charge is how much? That 92, and in the product already we have 92, right? This is a side. So this is 38 plus 54. This is nothing but 92, right? This is 92. So this x and y particle must be neutral, or like they can be both neutral particle, or their charges will be such that in like if we add the charges, both will make the total charge to be 0. That means see, either x and y both can be neutron, or one can be proton and another can be electron, so that like addition of charges will give you 0 for x and y. So these are the possibilities with the charge conservation. So with the charge conservation, we can see the total charge of x and y must be 0. And each case you look, if you see this, there are 2 neutrons, so this can be, see, from charge conservation we can just say this can be a possibility. So this, there, see, in the option B there are proton and electron, so we cannot distinguish these two. We have to further go with kinetic energy, etc. And then look this option C. This is by like a single site, or by like at a glance we can ignore this option, thinking this is wrong, because total charge of proton and neutron cannot be 0, right? It is giving some additional charge, which is not possible. So option C, we cannot think at all about this option C. Now we will go with momentum conservation. Okay, momentum conservation. Look this, kinetic energy of these two guys. See this X and Y, they have the same kinetic energy. Okay, they have the same kinetic energy, right? And initially this guy like uranium was rest. That means momentum. So linear momentum of xenon plus strontium plus this X plus Y, this will be zero by the law of conservation of linear momentum. Total momentum must be zero. So that is another clue we can get. Okay, let us see first of all whether the kinetic energy of strontium is 86 MeV or xenon has 129 MeV. That part let us first resolve. So how to resolve that part? First of all, let us see what is the change in the binding energy. Because look here, the binding energy is okay. I'll just clean everything. So the binding energy of uranium is given, and obviously binding energy of uranium per nucleon is less than the other two. That's why it is going to be like the most stable, okay, in this situation. So anyway, so the change in the kinetic energy, sorry, change in the binding energy, change in the binding energy will be manifested as the kinetic energy of all the product nuclei. Okay, the change in the binding energy will be manifested as the kinetic energy of the product nuclei. So where the kinetic energy of the X and Y are given, the kinetic energies of xenon and strontium we don't know. We have to calculate those. Okay. So look. So binding energy, change in the binding energy, change in binding energy, Be, will be, see how many nucleons are there for the uranium, that is 236. So we have to multiply. First of all, we need to find, okay, so binding energy of xenon has 140 into 8.5 MeV plus strontium has 94 into 8.5 minus 236 into 7.5. So if you do this calculation, you'll get 219 to be the total kinetic energy. So this will be the change in binding energy. Now change in binding energy, this is MeV. Change in binding energy will be manifested as the kinetic energy. So we know the kinetic energy of two products X and Y. So the kinetic energy of Xe plus kinetic energy of SR must be 219 minus 4. This is in MeV, which is 215 MeV. Now look, 215. See, if we add 1 to 9 with 86, so this will give you that. So this is total energy. You can see that. Okay. Now you have to now see See, xenon and strontium. Among these two particles, the strontium is the lighter one. See, the total energy has to be 215 MeV for xenon plus strontium. Okay, kinetic energy of strontium. So this much. Now we have seen there are options. Either it has to be 192 for xenon or strontium. And there is another option, kinetic energy of xenon or kinetic energy of SR to be 86. So now look, the strontium has mass, how much? It has mass 94 mass number, and this is strontium mass number, and xenon has mass number 140. So this is the lighter element or lighter nucleus. And you know, lighter nucleus will move faster. Okay, will move faster. So kinetic energy of strontium will be greater than kinetic energy of xenon. That means, you know, the kinetic energy of xenon will be 86 MeV, and that of strontium will be the other one, that is one, sorry, yes, 129 MeV. Okay, so 129 MeV. All right, so this is how we can see with charge neutrality. We can consider either. See, now we have options. So anyway, C we had already dropped, and D now we are dropping because kinetic energy of strontium will be more. Okay, so C, D we have already dropped. Now among these two, which one will be the correct one? We have to choose now. Okay, we have to choose. So C, D we can ignore. Now we have to see. Now we have to see among these two, like X. So this can be neutron, or it can be proton, and kinetic energies are same. So now how to distinguish from here? So if this X and Y are proton and electron, then what is the difficulty? Since the number of electron and proton before the reaction and after the reaction should be the same, number of proton and number of electron, to just maintain the charge neutrality, X and like both should be like number of electron and number of proton after reaction and before reaction must be the same. So if X is proton and Y is electron, then see we have in this reaction already we have number of protons and number of neutron. We can just find out. See, what is the number of proton? Number of proton is 92. So we have got number of proton 92 already. Okay, but again, if we have this as proton, so then the total number of proton will be 93. Okay, even though charge neutrality is there, but number of proton and number of electron separately has to be conserved. The number of electron and number of proton has to be individually conserved or separately conserved. So if this X and Y like X is proton and Y is electron, then the conservation of number of proton and conservation of number of electron is not satisfied. So that's why proton and proton and electron, we cannot take that. So therefore the option A will be the correct answer for this question. Okay. So we have now uh, yes, so we have now one last more question. See, this question says, an accident in a nuclear laboratory resulted in deposition of a certain amount of radioactive material of half-life 18 inside the laboratory. So this happens generally in nuclear laboratories and all. Due to radiation, there will be lot of havoc, uh, a lot of accidents. There is a permissible radiation. There is a permissible radiation if the radiation of any particular radioactive substance is more than that permissible value, then there could be accident. So generally when we are in the nuclear laboratory, there will be a small machine which will be given to each and every uh, workers or every individual, each and every scientist or any workers, to take just like a batch to see the count, okay, per second, or so there is a counter radioactive element, how many are penetrating our body, that will be counted. If this value goes beyond the permissible value, then it can uh, cause harm to our body. Okay, so that is the thing. So here question is, an accident in a nuclear laboratory resulted in deposition of a certain amount of radioactive material of half-life 18 days inside a laboratory. Tests revealed that radiation was 64 times more than the permissible permissible value. Okay, permissible radiation limit. Okay, permissible radiation limit for safe operation of the laboratory. So what does this mean? See, suppose the permissible value is n, or so this is how do we write that? We can write this as, see, rate of decay, radiation means rate of decay of the nucleus. Okay, so that we can write as r. So if r0 is the permissible value, then this r of t at any time can be written as 64 times of r0. This is the permissible value. Permissible uh, radiation. Okay, all right. So now r0, if the limit is r0, now it is 16 times of r0 more than the permissible value, as I said. Now, what is the minimum days after which laboratory can be considered safe for use? Okay, after how many days the laboratory will be considered to be safe to use. So to see that, what you have to do, see, we can find out R by R0. R by R0 is 64, right? So generally R is written as R0 into e to the power minus lambda t, kind of that. Okay. So we can actually write this as, and this is actually half lifetime. Lambda is written as 0.693 divided by t half. Because this is how lambda is written. And if we take the mod of this and see, if we take logarithm of both sides, okay, logarithm of both sides. So if we make it 10 base, so 2.303 logarithm of this is actually, if you take the magnitude, this will be lambda t. Okay, lambda t. So this can be further written as 0.693 by t half life. So I can write it here. So from here I'm writing, okay, this is r by r0, so it is minus lambda t. So I'm just ignoring the minus. Okay, so 0.693 divided by 18. 18 is the half life into t. Okay, so this part will give you, so 10 base log 84, sorry, 64 will give you, this is into 1.806 into 18 divided by 0.693 is the t. Now look this, if we solve this, we'll get, actually this t will be how much? We can simplify, just strike this out. Okay, maybe we can just, so 3 2 3 3 3 1, and this is 6. Now you can, okay, so approximately how long it will be, you have to just do the calculation part and simplify this value, this thing, then you must be able to get t is equal to 108, nearly equal to 108 days. Okay, 108 days. After that, it will be safe to use. Okay. All right. So this is the answer. So 108. This will be the answer here. So I think this is 2016 problem paper, 2016, not 15. I think that will be previous one also will be 2016. 2016. Advanced JEE Advanced 2016, the previous one also was there. Okay, so with this we will stop it here for today. We'll take up more questions from the JEE papers, advanced paper in the next classes. So thank you for your patience. Bye for today.